All right. So for our first main lecture, what we're going to be doing is going over some of the quantum mechanics that describe the systems we're going to be talking about. This may seem a little strange because we're not going to be doing a whole lot of quantum mechanical calculations in describing the actual bulk systems. But there are certain aspects of these materials which you kind of need to have the physical background to fully understand. So the main thing that we're going to be aiming for with this is coming up with how bands work, like energy bands. So if you've heard of valence bands, conduction bands, things like that, that's what we're going to be looking for with this quantum mechanical understanding. So to fully understand these semiconductors, we need to understand the quantum mechanics first. So remember, in quantum mechanics, we can describe probably like nuclei or electrons. For semiconductors, we don't care about the nuclei so much. We're going to only care about the electrons and then equivalently holes because they're going to behave essentially the same. So as a quantum particle, the motion of an electron is going to be described by the Schrodinger equation. And so you should use the time-dependent form of the Schrodinger equation, but you could do a little bit of math, simplify it. We're going to care only about the time-independent form, which is given down here. So there's a few different parts of it. So we have this part in green, which just is the gradient of the wave function. So hopefully you're familiar with what a wave function is. But if you're not, the wave function is essentially just a function. Usually it's like a sine cosine sort of deal that describes the motion of the particle. And then you can take the wave function squared or something like that, and you can get the probability density of finding an electron in any given spot. So that's what the wave function is. We're going to take the gradient of that. We're going to take this box in pink right there, which just has some constants in it for kinetic energy. Multiply that by this whole expression here, which just has the expectation value of the energy in general, and the potential energy, which is this U of X, Y, and Z portion here. That's all multiplied by this wave function. So all of that just equals 0. So that's the time-dependent form of the Schrodinger equation, dissected into parts. If you're unfamiliar with how each of these bits work, you can go into the textbook PRA, or there's some pretty decent resources online that'll help you understand it. But for our purposes, this understanding should be just fine. So we're going to start our sort of journey into the quantum mechanics by considering just a free particle. So this is just a particle, in our case, an electron, where it's completely free to move in all directions. The potential energy is 0 in all directions. There's no penalty to move one way or another. So what does that do to the equation? So in this case, there is no potential energy. So we just remove that potential energy term, remember, which is that U of X, Y, and Z. So we just remove that term, that becomes 0. Then we simplify the equation a little bit. So we just have the gradient, and then we have our energy term here. Then what we're going to do is, instead of looking at the gradient, which is going to be like dx, dy, dz, we are going to make our lives a little bit simpler. We're going to work only in one dimension, partially because the results are going to be sort of generalizable to each given direction. So we're just going to look at one direction. We're going to imagine a free particle that can move anywhere on like an x-axis. So if that's true, then the gradient only has one term in it, which is this one. So we're going to remove those dy and dz terms. So that gets simplified a little bit. So now we have the second derivative of our wave function here. We have our energy term with our regular wave function here, and then that's going to be equal to 0. Then what we can do is simplify even further. So there's a constant which is this one here, that energy is equal to h bar squared k squared over 2m. And so that's from the kinetic energy operator. And just to be clear, so energy is energy. This is going to be kinetic energy in particular. We're going to have h bar squared, which is going to be Planck's constant over 2 pi, and then square that. And then k here, that is equal to the wave number, which is like 1 over the wavelength. It scales directly with energy, and it's really important when considering the momentum of a particle. And then 2m down here, that is going to be the mass of our particle. So let's plug that in. So from before, we have our second derivative of the wave function. We have our kinetic energy terms. We have our new energy term. And we're going to just start canceling things out. So this h bar squared cancels this h bar squared. We have a 2m and a 2m. So when you cancel out all of those expressions, you just get the second derivative of the wave function with respect to x plus k squared times the wave function is going to be equal to 0. So from there, that is just a differential equation, right? So we have d squared plus no derivative is equal to 0. And I'm just going to go ahead and skip the differential equation, but it's a fairly well-known one. And the solution is going to be, it's going to be the wave function with is going to be equal to some constant, a plus, so there's a positive one, is equal to e to the ikx plus another constant, a minus, times e to the minus ikx. So there's two different components here. And that's the general, that is going to be our solution to a free particle for quantum mechanics. So that's cool. But we're not really working with free particles, right? We're working with particles that are in lattices, in atom or in solids. So let's continue by making things a little bit more complicated. So what we're going to do is start with the particle in a box formulation. So the particle in a box you have almost certainly come across before. It comes across in chemistry a ton because it looks a lot like an electron bound to an atom. And this is how you can get things like different energy levels out of, say, like a hydrogen atom. And you can start to derive like, oh, it looks like electronic lines or atomic absorption should just have like single lines of colors. And in fact, that's what we see. So this is sort of why we come up with this a lot. So let's solve this system now. So in this system, oops, there we go. So in this system, we're going to define that the potential energy is 0 everywhere except for outside of the bounds of this box. So x is less than or equal to 0, and x is greater than or equal to some distance a. So this is what our system kind of looks like. I've got a picture of it here. So within this box, potential energy is 0, and outside of this box, potential energy is infinite. So you might be able to see now why we started with a free particle, even though we weren't that interested in it, because inside this box here, where it's u is equal to 0, the equation should still work for the free particle because there's no potential energy. Okay, so let's start again. So we have our Schrodinger equation again. Notice that it's the k squared form, so we've already simplified it a good bit. And that is true for the bounds of the box. So 0 is less than x, which is less than a. And now, since the potential energy is infinite outside of this box, right? So as soon as you cross this line, the potential energy becomes completely insurmountable. So what that tells us is that the wave function becomes 0 at those points. the particle cannot be there. So since we defined the edges of our box and like our boundary conditions to start at x equals 0 and x equals a, once we have the wave function at 0 and the wave function at a, both of those have to equal 0. So then we do a little bit of differential equations and we get the form, and the wave function is equal to a sine kx and b cosine kx. So that's sort of like the general solution that we have. But then we're going to apply those boundary conditions. So the first one is that at the psi of 0, the solution has to be 0, right? So sine of 0 is just 0, so we cross that out. Cosine of 0 is 1, which means that b has to be equal to 0. Okay, so we just solve this equation here. We apply this boundary condition, which is that psi of 0 must be equal to 0. The sine component is already going to go to 0, so we have no information on what a might be. But since the cosine is 1, b must be 0 in order for that boundary condition to hold. All right. So now we're going to apply our second boundary condition. In this case, that psi of a has to be equal to 0. So here, psi of a, we have equal to a sine ka plus b cosine ka, but we already know that b is 0. So this component just falls out of the equation anyway. So at psi of a, we just have a times sine ka, which is equal to 0. Now, this is going to give us something that's a little bit more complicated than just like a is equal to 0. So what we get is that that condition is only satisfied when k times a, remember this is k, the wave number, times a, the width of the box, is a multiple of pi, right? Because we get sine of, I believe it was, yeah, it's sine of 0, pi, 2 pi, all that sort of thing. Those are all going to be 0 if you remember your unit circle, where for cosine it's the other way around. So it has to be a multiple of pi. So k is now restricted in its possible values. So k is going to be equal to n times pi over a, where n is going to be equal to plus or minus 1, plus or minus 2, plus or minus 3. Because remember, it can be either plus or minus pi. Either one works. So if we apply that, our wave function for the particle in a box becomes equal to psi of x is equal to some constant a, capital A, times sine of n times pi x over a. So where, of course, n is plus or minus 1, plus or minus 2, plus or minus 3. Now, the allowed energies are also restricted. Because remember from before, the energy is going to be equal to h bar squared k squared over 2m. And we've restricted k, right? K has to equal this n times pi over a term. So we combine those terms and we get that the energy is equal to n squared pi squared h bar squared over 2m a squared. So the important part here is that E is going to be proportional to n squared, right? And n has restricted values. It has to be an integer number, either positive or negative. And so the energies have to be these discrete values. Also interesting is that it's n squared. So remember we had like n equals plus or minus 1. Well, from this we see that if n is equal to plus 1 or n is equal to minus 1, the energies are going to be the same, right? Because we have the same n value, or we have the same n squared value from those n's. So that has led us to these energy levels, which our particle is allowed to occupy in our box. right? So that's the big takeaway from particle in a box quantum mechanical systems, is that once you confine a quantum particle, there are only certain energy levels that it's allowed to occupy, where if it's in free space, it can do kind of whatever, right? It can be at whatever energy level it wants. In a restricted system, especially for particle in a box where you have infinite energies on either side, there are very defined energy levels that it can be in. Okay, so we have looked at sort of a free particle system, which is a nice little toy example. It gives us some fundamental framework, some fundamental math to work with. And now we have looked at the particle in a box, which is pretty common in chemistry. We've seen it all the time, but we're working with solids here. So we're not working with an individual particle in a box system. We're working with tons and tons and tons of particle in a boxes next to each other, right? So we're going to look into a periodic system. So what does that look like? So we're going to, again, start simple. We're going to imagine that there's going to be a one-dimensional array of atoms that are some constant distance apart. We're going to call that distance a, lowercase a, just like before with our particle in a box formulation. So that's going to look sort of like this. So we just have a whole bunch of atoms separated by some distance a, just an infinite line. Okay. So what does that potential energy landscape look like? So the energy as you approach the atom, so this is for an electron, as you approach the atom, the potential energy is going to approach negative infinity, right? Because this makes sense because for an electron, it wants to be close to the atom, right? You know, you want to bind electrons to the atoms because you have like the positive nuclei. We're going to ignore the fact that, you know, when you get too close to the atom, things change. But for our toy example, as you get closer to the atom, it gets more and more favorable for the electron to be there. So that is going to have a potential energy landscape that looks like this graph here. So the potential energy goes down to negative infinity as you get closer and closer to the atom. So you can see like there would be an atom here at x equals 0, one at x equals a, one at 2a, etc. Also note that if there's no atoms here, the potential energy goes to 0, right? That goes to 0 because it has no willingness to be one place or another. So what you get is sort of these like sort of parabolic shapes, right? As you get closer and closer to the atoms. So this formulation falls under the jurisdiction of the, I think it's Bloch theorem. I'm going to say Bloch, but I might be mispronouncing that. So this is a quantum mechanical and a periodic system theorem that sort of states that if the potential energy is periodic, which ours is, such that u of x plus a is equal to u of x. So what it's trying to say there is that like if I have some point here, so that potential energy is going to be some value here, right? We'll just call this u is equal to, I don't know, q. And then we add a. So we're going to add a. We're going to move it over here. We see that the potential energy is still the same. U is still equal to q, right? So that's what it's saying there, that our system is periodic. All the energies there are the same if you add a. Then in that case, psi, so the wave function, x plus a is going to be equal to this factor here, e to the I k a times the wave function x. So let's look at what that means. So this is just like some theory in here. So psi of the x plus a is equal to e to the I k x plus a times the potential energy of x plus a, which is going to be equal to this guy there. And then if you actually combine these two, you'll get this function here. So not super complicated, not super important, but just in case you were wondering sort of how this comes about, this is the equation that lets that happen. Okay, so if we have this formulation here that the wave function at x plus a is equal to this factor times our original wave function, notice now that the wave function itself is periodic, right? So at any increased value, like if you increase your position by a, you're going to be exactly the same as the wave function at a different point, just with this factor of a in it. So the wave function is now periodic. So now we can make a few generalizations regarding the values of k. So for a one-dimensional system, there are two distinct values of k for each allowed value of E. So there are two distinct wave numbers for each allowed energy. This is for a 1D system. In 3D, it's going to be a little bit different, but for our understanding, this is fine. Then for a given energy, the values of k differing by a multiple of 2 pi over a will give rise to the same wave functions. So that's really, really important. So what that means is that k is limited to a range of 2 pi over a. In other words, it's never, even if you have a value of like k is equal to 2 pi plus a plus 1, just add something to it. The value of energy is going to be something we've already seen somewhere in that range of 2 pi over a. So it's not useful to define any k's outside of that because all the energies are going to be the same because it's a periodic system. Now, if we assume that the periodicity is infinite, which we will for simplicity's sake, the only other restriction on k is that it has to be real. So this leads us to our final revelation regarding k, which recall is the wave number related to energy and also particle momentum, that we can now approximate large finite crystals, we can approximate large finite crystals with periodic boundary conditions. So the periodic boundary conditions are going to approximate our system as like a closed ring with some spacing a. So in other words, if you start at some point A and you go all the way around, you're going to come back to point A, and you're going to have the exact same value that you did the first time. So that's going to work fine for periodic systems. So let's define mathematically what that means. So we have our wave function at x is going to be equal to the wave function at x plus some number n. So like, remember we have an n atom ring times a. So what this is saying is that if we have this here, so this is going to be psi of x, and this is going to be psi of x plus 1a, and this one's going to be psi of x plus, x plus 2a, and so on and so forth. So what we're doing there is stating that the wave function at some given point is going to be equal to the wave function at some other given point that's a multiple of n times a away. So that gives us the form e to the I, k, x, and a times psi of x. Remember this factor we've seen before, we've just now added this capital letter n. So that actually ends up requiring, note, that if this is going to be equal to this, the only difference here is this factor. And that means that that factor has to be equal to 1. So what we'll do is make that factor equal to 1. So you can do a little bit of math. Remember, you can do like the Euler formulation to split it up into sines and cosines, blah, 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 blah. And you end up with another restricted k. right? So K is going to be equal to 2 pi times N, little n over big N times A. So remember, big N is the number of atoms in your system, where little n varies from 0 to plus or minus big N over 2. So that's sort of the block theorem. And so what we get out of that is that, once again, our K values are restricted. They're just restricted in a different way. And what we're going to, so the block theorem is nice. It does a decent job describing how we expect a periodic system to behave, but it can still be a little tricky to solve. You might notice here, I'll just use this one here, that we have like these sort of parabolic systems here, which can be a little tricky to get the actual math right. So we're going to simplify it even further. So what we're going to do is simplify with the Kronig-Penney model. So now, instead of having these parabolic shapes that approach negative infinity, we are going to have a periodic array of finite potential particle in a box systems. So remember, with an infinite potential particle in a box, the atoms cannot exist outside of that box, but with a finite potential, they can. They don't have a high probability of doing so, but they can. And that's going to approximate this sort of parabolic system that we have here. Just like we found in the normal finite well, there are distinct solutions, and the block theorem lets us work with an arbitrary unit cell of length A plus B, which I'm going to get into what that means here in a second. And we're going to simplify by choosing these X points as the unit cell boundaries. So from now on, the subscripts B and A, and I'm trying to use different colors as well, will identify the wave functions and solution constants in the regions B and A. So now there's going to be two different regions, one where you have a potential, like there's a potential energy to be in that region, and there's another region where there is no potential energy to be in that region. You're a free particle. So this is what it's going to kind of look like. So if we have a graph of potential energy versus position, we have our unit cell here, which you can see just gets repeated over and over and over again, which is why it's our unit cell. And we have B, which is going to be our region where there is a potential energy. And then we have A, which is our region where there is no potential energy, where you're a free particle. Thus, what we're going to do is solve the Schrodinger equation for A. So we're going to get this second derivative of the wave function plus some factor A squared times the wave function is equal to 0. So remember, this is just essentially the free particle. And alpha, which is our constant here, is going to be equal to that factor there, square root 2m times e over h bar squared. Now, for B, the region where there is a potential energy, we're going to do this again. We're going to act sort of like it's a free particle. It's just got a fixed potential energy. And beta now gets a little complicated. So we just have this factor here. But if you split that up, depending on the energy and whether the energy is greater than or less than the potential, which is defined right here. So that's our maximum potential energy. Beta is going to assume a different value. So you might want to just write these down. They're a little complicated, but you get this from just solving quadratic equations. So we're going to do a little bit more math that we're going to skip over, get the general solutions, which are psi of A. So this is no potential times X is equal to some constant, sine alpha X, B cosine alpha X. These should be familiar forms. B is going to look very much the same. So the wave function and its derivative must be continuous at x equals 0, right? Because these are periodic systems. We want them to just flow right into each other, right? It wouldn't make sense if we just have these hard jumps in energy in between our unit cells. So they have to flow into each other. They have to be continuous. Plus, the wave function and its derivative evaluated at the cell boundaries have to obey the periodicity requirements, which we've already talked about. So what this leads to are 4 what are called boundary conditions. So there are 4 conditions that these equations must fulfill in order to be valid for our formulation. So like before, there's the continuity requirements, where not only are we going to define that both the A and B are going to be 0 at x equals 0. And recall the way we defined x, we're going to have B being, I believe it's a little bit below, A is a little bit above, but they're both going to be 0 at x equals 0. And then the derivatives are going to be equal to one another. Now for the periodicity, just like before, we have this wave function for A is going to be equal to e to the ika plus B, because remember, that's the width of our unit cell. So we're adding a unit cell here, is going to be equal to now actually a portion of the wave function at B. So if you go back and look at the graph, you can see that this sort of makes sense. If you take spot at A and we add a whole unit cell, it's going to look like negative B. Similarly, the derivative is also going to be equivalent as we add a unit cell here. So what this is letting us do, this is allowing, these boundary conditions allow the equations to sort of flow into each other, right? So that you don't have like a hard jump in energy, because that doesn't make a whole lot of physical sense. And the periodicity kind of gives us our symmetry, right? So it makes sure that like this point is going to be equal to that point. All right, then you do like kind of a lot of math. We're not going to worry about that. It's not important. This is not like a math class. If you're interested, it's these equations in pure A, 3.15 through 3.18b. So you can see this is really exciting. When you solve it, you get a graph like this. You get this new, like, I forget, it's just like an eta or a zeta or something. I'm terrible at drawing them. But that little squiggle there is actually, it's just energy. It's like a normalized energy. This is what it is equal to. The zeta is equal to the energy divided by the maximum potential energy. So just have this be like the function of, so the solutions of these equations with respect to this normalized energy, and then this is just energy. So we're seeing where it can be as a factor of energy. So you get this kind of graph here, but because we have defined that K has to be in this certain range in between 0 and plus or minus pi over the length of the unit cell, we can actually carve out certain areas of this function which are allowed to exist. So what you do is you kind of draw a line for K is equal to 0 here, and you draw a line for K is equal to this thing here. And you see that there are certain spots where the electrons would be allowed to be. I've shaded those in. And you also see that there are certain areas where the electron is not allowed to be. So remember, this is from applying our restrictions to K, because we have these finite energy systems. And remember, like the K at one spot has to look like the K at another. Our electrons can only occupy these certain bands. Notice that they're like more or less continuous here, so they're not like, individual lines. They're actual bands of energy. And there are areas where they cannot be. So we call the shaded regions here energy bands, and we call the regions that are not shaded band gaps. All right, so in order for an electron to start, say, in this energy band and go to this energy band, there is an energy penalty. It can't like make a trip and like stop here. It has to have all the energy it needs to get into that band. Okay. Now we're going to sort of like flip this on its side and plot the allowed energies as a function of K. So again, recall that this eta zeta thing is just a normalized energy. So we're going to start with it. It looks like this. I cut off the parts that are sticking out. So these are just sort of our bands here. Now notice this is equal to K equals plus or minus here. So what we're going to do is flip it on its side. So now I'm going to convert that eta into just like an energy, right? Same thing. And we're going to have it plotted as a function of K. So it goes from 0 to plus or minus pi equals a plus b. So what we're going to do is we're just going to kind of mirror it. So it's going to go from minus that bit pi over unit cell to plus pi over unit cell. And so when you do that, you end up with a graph that looks like this. And so this is called an E versus K diagram because you're plotting the energy as a function of K. So energy is a function of wave number. And notice you still have these bands here, right? So that's an energy band. And that's an energy band. And then there's a band gap in between them, right? So that's what we get from E versus K diagrams. So they are like super important. There's something we're going to come across quite a bit in this class, but at this point, you've done all the math to derive that energy bands exist and that band gaps exist. So as sort of a summary, what we did is we reviewed our basic quantum mechanics, which we probably learned in PChem, and we applied it to periodic systems. Then we looked at the Bloch model and the Kronig-Penney model as simplifications for those periodic systems. Remember, the Bloch sort of tells us that as you get closer to the atom, you get closer to negative infinity, and that sort of gives us these restrictions on K. And then the Kronig-Penney just allows us to do the math a little bit easier. And then using the Kronig-Penney model, we constructed an E versus K diagram and saw how it led to energy bands and band gaps. So now you should be able to look at an E versus K diagram and say, okay, so these are different energy bands that you're allowed to be, that an electron is allowed to be in at different values of K. There are regions where the electron's allowed to be, so that's in here. And there are areas where electron is not allowed to be. So that gives rise to our band structure that's going to give us all sorts of interesting properties about semiconductors. So I will see you in the next lecture.